Alright, so today we're going to go over how to solve problems when the situation is presented to you where the object is on a slope. Something we haven't done yet. It may look like it could be a little confusing, but we're going to utilize a little trick that actually simplifies the problem back to what we've already been doing, just to make everything a little bit easier to do. So with every problem, we're going to first start off with by identifying what values are given to us. So we have a 60 kilogram skier. That means we know our mass. Pulled up a 30-degree incline. That angle's already there. Now the maximum tension the rope can handle is 400 newtons, so that means we're going to have an FT that maxes out at 400. And with what acceleration, maximum acceleration really, so we are looking for a value. And then we're going to assume no friction due to snow and ice. Now in reality, there is going to be friction even with snow and ice. It's something like a mu value of 0.04. It's really small, but it's still there. All right. And we kind of all experienced that this morning. It's not non-existent. It's there, but sometimes it's pretty low. So the first thing we do after doing all of this is then create our free body diagram. So for our skier, we have gravity acting straight down, as with every example. We have our tensional force acting in the direction of the rope, which way it's being pulled. And we have normal, which is perpendicular to the surface. So I'm drawing that up and to the left. And all the problems we've done so far, normal was straight up. And that's because the surface was flat, and perpendicular would be vertical. Now, as that incline, that slope starts to increase, you're going to notice that f of n, since it has to be perpendicular to the slope, is going to rotate to point more and more to the left. It's going to be more and more in that negative x direction. So now we have a free body diagram. We have step 1 done, but we actually want to break these forces into components like we do normally. We need to break these into x and y components. Now, if we were to do that in the normal sense, we would have an FTX. We would have a force normal in the x direction. And they would also have y values for all of these as well. So an FTY and an FNY. And we just went from having 3 forces to now having to deal with 5. Now, luckily in this problem, it says to assume no force of friction. Now, if we did have a force of friction, that force of friction will be opposing the direction of motion. So if this thing is moving up and to the right, friction will be down to the left. Now, if friction were down left, we'd have to introduce another x component and another y component. So we went from 4 to now 7. And we can avoid that by doing a little trick. We can take our problem, and if you remember from back at the beginning of the year that you have a reference frame or a frame of reference, we can change how we're looking at this problem. Instead of looking at it from this perspective where we have a 30-degree angle slope, if we take our perspective and rotate ourselves 30 degrees, we can make that slope flat. We'd have normal going up, tension to the right, and now force of gravity would be down to the left. What that does is that means that we only have to worry about breaking gravity into components, not both of the other forces. So we're going to have an FGY and then an FGX. Now if we were to rotate that and draw it in the perspective that we normally use, that would mean that Fn is directed upward. Force of tension is to the right. Fgx is going to be to the left, and Fgy is going to be directed downward. So now the entire free body diagram is in the perspective that we're used to, just seeing a plus sign with our forces either in the x and y directions only. But now that we have these values, we should start plugging some of these things in. Now the only value we can plug in as of right now is the force of tension, because we said that that has a maximum of 400 newtons at which the thing can handle. Now the FGX and the FGY would be where we need to go next. Normally we would just take the mass of 60 kilograms, multiply that by 9.81 and get the weight of the object, our FG value. But since the FG is now components, we need to break that up. The equations are given here. You have the FGY equation and you have the FGX equation. Those are very similar to the velocity equations we used, where Vx is Vt cosine and Vy is Vt sine. The difference here is this angle theta. Because of where theta is and the orientation of it compared to our FGX and FGY, that means our y component is now the adjacent side, our x component is the opposite side. So we use cosine with our FGY component, and we use sine with our FGX component. Now I could tell you the explanation of that, and if you want to know that, stop in tomorrow during my office hours. Otherwise, just take my word for it, because that's going to take a few minutes to talk about. But the reasoning is geometry. So I'm going to go ahead and solve through FGX, FGY, plugging in the values, and you go ahead and work along with it. So the values we have then are FGY of 509.7 and FGX of 294.3. So plugging those into our diagram. And the only thing we have on here that we don't know yet is going to be that FG, or the FN value. Sorry, I forgot to delete a little bit of editing magic that happened, because this is two separate videos. We need to now figure out what that FN value is. Now normally we would say that Fn is going to be equivalent to Fg, which would be true if this were a flat surface, but since it's at an angle, gravity isn't pointing directly into the ground, it's acting in a component sense. So the FGY is the value that we need to be concerned with here. That is what's going to be equivalent to our force normal. So that's where this equation, the Fn equals negative FGY is. So our Fn value here is going to be 509.7 newtons. Now here I have it written as, you notice the FGY is 509.7. And you would think that Fn then needs to be a negative 509.7 based on the equation that's there. Now recall that the FGY and the FGX are both acting in the negative directions in this sense. The negative x direction for FGX and the negative y direction for FGY. So that's why that FGY should really be a negative 5097 and the FGX will be a negative 294.3. So the next bit here is step 4 is missing. Step 4 would be solving for the F net in the y direction. Now the F net in the y direction is going to be our Fn plus our FGY. Said our Fn is the 509.7. Our FGY is negative 509.7. And we get a net force in the y direction of 0. No, that makes sense because the skier is neither floating off into space nor are they sinking into the snow. Okay. The next step would be finding the net force in the x direction. So that one is going to be the sigma fx. That's going to be our x values, which is going to be the force of tension and the force of gravity in the x direction. Plugging those in and then solving gets you the following. It gives you a net force in the x direction of 105.7. So that's the sum of our x components. Our y's canceled out, got a 0, our x's did not, and gives us a total net force of 105.7. Now that answers our first part of this. Or what is the maximum acceleration? The question that really was asked at the very beginning of this, what is A? To find A, we go to our net force equation, Newton's second law, F equals ma. Since y is 0, then this sigma f is just going to be the x component value. So 1057 you get an acceleration of 1.8 meters per second squared. That is the maximum acceleration that can be achieved by the skier up the slope, given that the maximum tension on the rope is 400. So if this maximum tension were less than that, that would yield a lower sigma fx, or net force in the x direction, which would yield a smaller acceleration. Another thing that would cause issues here is if this slope increased, right? This slope would be increased, the FGX value would increase as well, which would mean that this component here would go up, which would decrease the net force, which would decrease the acceleration. So look at these problems. We have the steps that are up here to the left. They are diagram, we're going to rotate, we're going to re-diagram, going to solve for the FGX and FGY, then do our net force components, then after that you solve for whatever else there is. Alright. Now these steps are basically the same as our other problems. We always start off with diagramming, then we go ahead and then we go to our net forces. So we're only really adding these 3 steps here. The other steps that were there to begin with. Alright. So now what you're going to want to do is there are some problems on Google Classroom for you to go ahead and work through. It's going to be off of that worksheet we did a couple days ago where I had you skip numbers 8 through, I believe, 11. Those are the ones where objects were sitting at angles. If you haven't done the other one yet, go ahead and get that done because the solutions to those are going to be getting posted here later today. And you're going to want to make sure you have your own take on what you're doing first. You don't just want to wait for those solutions to show up, okay? And also make sure those are submitted through the classwork tab. Now those 8 through 11, they will be due here later on, just like the other ones are. Make sure those are into Google Classroom, and then shortly afterwards, the solutions to those problems are going to pop up. Okay? Well, have a good day.